Professor Claude LECOMTE is full professor of physics and crystallography, and Claude is retired since February 2013. He has established in 1995 the CNRS University of Lorraine LSM3B laboratory. At that time, at first it was called CRM2 laboratory for crystallography, magnetic resonance, and modeling, which he directed from 1995 to 2013. Claude was always very open person, full of ideas and different initiatives. And among others, he kept inviting scientists from all over the world. So many of us, including Anya, Paulina, and myself, spent at least a month or longer at Nancy in his lab. Claude published more than 420 scientific papers, which have more than 16,000 of citations. He was the head of this lab for more than 20 years. He has been commissioned for evaluation of crystallography, solid-state physics, and physical chemistry scientific projects and laboratories across France, Europe, Japan, and USA.
Claude's primary interests lie in charge and spin density analysis by accurate X-ray and polarized neutron diffraction. This includes experiments, methodology, and instrumentation, including pixel detector developments. Applications to perovskites, zeolites, molecular materials, magnetic or non-magnetic, models of hydrogen bonds and intermolecular interactions, proteins, phase transitions, etc. Crystal structures of porphyrins and cyclines until 1998, and the many other classes of compounds. In 2010, Claude was laureate of the European Crystallographic Association Max Perutz Prize. From 1980 to 1981, he was a naturalist doctoral fellow at Professor Philippe Copin's lab at Buffalo, New York, US. From 1998 to 2001, he was the vice chair and chairman of the Gordon Research Conference, Electron Distributions and Chemical Bonding. From 1997 to 2001, the president of the association, Francis de Crystallography. In 2000, he was the chairman of the ECM19 conference. This is a European crystallographic meeting. From 2000 to 2003, he was the president of the European Crystallographic Association. From 2009 to 2011, member of the executive committee of the IUCR. From 2012 to 2014, the vice president of IUCR. And from 2014, Claude is the chair of the IUCR Crystallography African Initiative, and also recently from 2021, the chair of the CNRS Aframed Research Network.
And Claude is the co-author of plenty seminal papers which actually shaped the field of experimental charge density over the years. And let me just mention selected topics of a few of them. So first, studies of hydrogen bond strength by topological analysis of electron density, studies of the nature of halogen-halogen interactions, joint refinement against X-rays, polarized neutron diffraction data, and magnetic Compton scattering, leading to spin-resolved electron density. First electron density database of multipolar parameters that was established in 1995, and reconstruction of electron density in crambin and aldose reductase family of proteins. First use of CCD detectors for charge density analysis and pixel detectors for accurate crystallography, and many, many others. Claude also edited in 2017 a special issue on electron density distribution that was published in Acta Crystallographica B as an honor for Philip Coppens. 25 manuscripts were published, and he joined this special issue with Jason Benedict and Yusheng Chen. And what is particularly worth stressing is promotion of crystallography in sub-Saharan Africa. Claude is the chairman of the IUCR UNESCO Africa initiative, which aims at developing structural and crystallography sciences in African universities. And in collaboration with the basic science departments of UNESCO and the IUCR, he has developed a new teaching concept that was launched for the International Year of Crystallography, that was 2014. And the initiative is called IUCR UNESCO Open Lab. An Open Lab is a workshop in crystallography with hands-on possibilities on single crystal and or powder diffractometers. This has been made possible thanks to the collaboration with diffractometer companies who lend for free the machines.
Claude is also particularly involved in the teaching of crystallography in Africa, in countries like Cameroon, Ivory Coast, Senegal, North Africa, Benin, Congo, Gabon, Togo, Egypt, Ghana, Congo, Brazzaville, where he organized and taught crystallography open labs or schools. Claude also launched experimental crystallography laboratories in close collaboration with IUCR, UNESCO, International Council of Scientific Unions, and Bruker Company. Bruker donated second-hand diffractometers, which are now installed in Ivory Coast and Cameroon. Claude also was the initiator and chairman of the first Pan-African Crystallography Conference in Chang. I must say that I personally really deeply admire Claude's initiatives. This is about delivering knowledge and expertise to African countries rather than engaging in post-colonial extraction of the most talented young people from those countries. Claude, the screen is yours.
Thank you very much for this very nice welcome for me. So hello everybody. I would like to thank the organizer and all of you who will attend this webinar. My talk will. Do you see my first slide?
Yes, we do.
So my first slide is the name that you see, the Place Stanislas in Nancy. In the bottom of my slide, and the title of my talk will be Charge Density Research, Past, Present, and Future, Challenge for Crystallography. So what will we speak about? We will speak about charge density modeling, which in fact is finding the best models of the atomic scattering factor, f of h. This atomic scattering factor, as you know, is a Fourier transform of the electron density, which formula is just below. As you see, we are interested in modeling the electron density due to chemical bonding. Then it will be mostly the valence electrons which are interesting for us. And so we are trying to find the best model of the valence scattering of all atoms involved in chemical interactions or physical interactions. Okay, so our electron density studies began a long time ago, because even in 1918, Debye was trying to show that a sodium chloride and potassium chloride were ionic compounds. And in fact, given the few possibilities he had in experiment, he was succeeding. In 1924, Hartree was the first to do some scattering factor calculation, independent atom, as you can imagine, model. And as you see here, we have some of the scattering factor table for the sodium and chlorine here. Then after, a very important paper was given by McVinney, who was one of the first to speak about non-spherical atom calculation in order to take into account the interaction between atoms in crystals. Konobievsky also was one of the first to use multiple analysis to study the aluminium. And then in 54 to 57, Schmidt-Hirschfeld were doing the first electron density analysis on phenazine. Dawson then measured absolute scale structure factor intensities for silicon and diamond. And in 67 also, Philip Coppens published his famous paper, science papers, which shows the first deformation density map by the X-N method. A very, very important breakthrough was in 68 with Bob Stewart, who published a paper about the generalized X-ray scattering factor, which in fact is coded after in the Valray program. In 71, Hirschfeld showed that we can also model the electron density by an expansion as a form of cosine to the power n theta. And in 76, Hans and Coppens published MOLI program, the multiple expansion of using the MOLI program. And then now we have MOPRO and XD to continue to analyze our electron densities. That was the first X-N refinement of Philip Coppens, who in fact combined neutron diffraction with X-ray. He was able, so what he did, he was refining atomic coordinates and anisotropic displacement parameters against neutron diffraction. And these parameters were used as starting parameters for the electron density analysis using, naturally, the X-ray data. And here is the first deformation map, which is an X-N deformation map, where you very well see here the lone pair of the pyrazine molecule. The first multipolar or aspherical analysis of the electron density, as I told before, was done on aluminum crystals by Konobievsky in 51. Then Weiss measured absolute scale structure factor for diamond and germanium, and was the first to say some success, he had some success in accounting for the lack of spherical symmetry of diamond by using an octupole, which is XYZ over R3, using this octupole. Then after Dawson, Kurki-Sonio, and Stewart continue the work to analyze the non-spherical electron density. In 68, very early in fact, Bob Stewart proposed a least square analysis of simple molecules, including two centers scattering factors, and the bipolar. It was developed, as I told before, in Valray program. That is his fundamental paper of Bob Stewart about the generalized X-ray scattering factor. For those who are coming in the field, I really recommend you to read this paper, which is a very important and very full of knowledge and ideas paper. On the experimental side, in fact, the important thing was to have to do low temperature experiments. And Hirschfeld, around 1957, designed a Weissenberg camera. Here is the Weissenberg camera, equipped with a low temperature nitrogen low temperature device. As you see here, the crystal is there, the gas flow comes like that, the X-ray field, the X-ray beam comes perpendicular to the figure here, and here the camera, the film around, which collect the X-ray data. He was able, with this low temperature experiment, to make the first delta rho maps, deformation density map, and showed in these maps the hydrogen position, as you can see here. We also see a little deformation density on this 57 dataset. Then, to get an electron density model, we need to have more accurate data. And the more accurate data came with the 4-circle diffractometers, even 3-circle diffractometers before. From Nicolet at the time, non-use, CAT4, with low temperature system, nitrogen low temperature, and even helium temperature system, made, for example, by Hakon Hope and Stevens, Philip Coppens and Bob Blessing, Finn Larsen, and Ricardo Destro, who were using helium cooling for having better data. One of the most important things for our field is to get excellent data, excellent structure factor, excellent quality structure factor. And Bob Blessing was a pioneer in analyzing the data with his integrated data reduction and error analysis software, which was in fact which is now used by everybody. Even the software we have from the manufacturer are in fact prolongation of Bob Blessing work. And then the first comparison between experiment and theory was done in 1978 by Stevens and Coppens on formamide. In that time, we had no static density maps. So what they have done was in fact to calculate theoretical density thermally smeared and compare this thermally smeared theoretical density to the experimental density derived from X-ray diffraction. As you see here is the theoretical density on formamide. You really see very well the lone pairs, for example, here. And here is the difference between the theoretical density and the experimental density. And what they concluded at that time, that the theoretical density was slightly lower in the CO and CN bond, and that the experimental density in the lone pair region is lower in experimental maps, which we can in fact understand very well because the resolution at that time of the map was not good enough. So during the 70s, we saw the development of the multipolar formalism and the excuse me, and the first static electron density maps. So when you have, for example, sp2 carbon, if you make the deformation density, which is the inverse Fourier transform of the observed structure factor minus the calculated one with the spherical hypothesis, you see this kind of feature with bonding density on the bond here and depletion of density between the bond. And as you see, this kind of map can be modeled by an atom-centered electron density, which is in fact the product of a radial function, which is a Slater function, times an angular function, which very often was chosen as spherical harmonics in real form. That was applied by Bob Stewart in Valray, Hirschfeld using cosine to the power n function, and Hansen Coppens in Molly. Kurkis-Sonio was also very active at that time, but doing direct space integration of the electron density. So I recall you very quickly the Hansen multiple model, Hansen-Coppens multiple model. For each atom, we select a frame on the nucleus of this atom, and the electron density is the sum of three terms: core electron density, valence electron density, and non-spherical electron density, spherical valence electron density, and non-spherical valence density. You refine in this model the valence population, which gives you the net charge of the atom, the expansion of the valence population with the kappa parameter, and the non-sphericity of the electron density with the spherical harmonics in real forms. For example, if you want to model that, it's easy to see that the noctuple here fit perfectly this deformation density here. So Mohamed Souassou, in his PhD in 1989, was one of the first to compare, in fact, the experimental density to Hartree-Fock calculation. For example, in a peptide group here, and you see what we have done is to calculate the dynamic deformation density and compare it to the Hartree-Fock calculation made at that time by Marc Bénard and co-worker. And you see here the very good agreement between the two maps. But to have this good agreement, he showed that we need to have a triple zeta basis set as shown below. As you see here, that is a comparison of bonding densities in the peptide plane with two basis sets. That's the experimental density. Basis set 1, which is a double zeta basis set, and basis set 2, which is a triple zeta basis set. And you see that even at that time, the experimental density fit very well with a very high level calculation at that time, triple zeta basis set calculation. The double zeta was not enough to reproduce the electron density. So at that time, charge density, experimental charge density were used mostly to test the theoretical electron density calculations. In 92, with Virginie Pichon and myself, were able to collect data on a 5 peptide unit molecule crystal, the leucine enkephaline, which it was at that time the largest electron density studies. It was both a challenge for experiment and theory. Here is, for example, the experimental density, showing a hydrogen bond here compared to this one. But for the experiment, the duration of the experiment was 95 days, using a point detector on a non-use CAT4 with a gas flow system. As you can imagine, at that time, we had a lot of problems to solve: stability, data reduction, and even on the theoretical side, Bénard and Romer had to take a smaller molecule like le enkephaline to, in fact, compare to the experimental density. That was published in 92 in Journal of American Chemical Society. You see that at that time, having a very good electron density, it was easy with a very good electron density study to publish in the Journal of American Chemical Society as a preliminary communication. If we look now to metal-ligand interaction, one of the pioneers was Bernard Ress and Michler, who were able to map the electron density of chromium carbonyl, hexacarbonyl here, as you see here, where you see very well the lone pairs of the CO ligand and the depletion of the d electron along the bond. He worked also on Mn2Ca, but later. And then the one very important thing was what Ed Steven did. It was the first estimation of d orbital population on a cobalt porphyry. He was able to show a relationship between multiple population to d orbital occupancy, and that was applied for the first time to a tetragonally distorted octahedral field. That has been published in Electron and Magnesium Densities in Molecule and Crystal, edited by Pierre Becker in 1978. But this book, which is full of very important theoretical chapters, is still a reference in our field. And at that time also, Tanaka and Figgis proposed d orbital refinement. For example, we were able to, in fact, check the theory on a big molecule at that time on iron porphyrins, which in fact was a tetraphenol iron porphyrin linked by two ligands, which were THF molecules. And when we do the calculation with Benard and Romer, the theory shows that it was the same energy for the two states, 5B2G and 5E2G. And our experiment showed without any problem that, in fact, the 5E2G was the good state for these porphyries, because the d orbital population are very close to what we get from the experiment. That was one of the first validation for the electron population. Very interesting review has been written by Philip Coppens in 1989, and I think it's very interesting to read it. I recommend you to read this review. I'm going now to see what we can do looking to electrostatic properties. The pioneer in that work was Berthaud, who in 1952 was able to calculate electrostatic potential from Fourier transform in ionic crystals. Then Bob Stewart, one more time, in 1979, calculated the electrostatic potential from Fourier, but also from multipolar analysis. Moss and Feil calculated also from X-ray data the electrostatic energy in 80, as well as Coppens and Moss. Craven was one of the first to use the electrostatic potential to describe the hydrogen bonds in 85. And we, in 88, wrote the electros program, Germany and myself, to analyze the electrostatic potential in peptides and coordination compounds. That is one of the a paper published by Berthaud in 1952, who describes the electrostatic potential, the electrostatic field, and the field gradient from X-ray data. My first interest for electrostatic potential calculated from X-ray data came with discussion with Bob Stewart at the beach during the excursion of a Sagamore conference in Luso Coimbra in Portugal. And as you see here, was written by Bob Stewart, how you come from the molecular electron density to the electrostatic potential by Fourier transform. That was done in the beach with a small pen that Bob Stewart had always with him. Craven, as I told before, was one of the first to use electrostatic potential to characterize intermolecular interaction. As you can see, at that time, he showed that, in fact, when you build the electrostatic potential of a cluster of molecules, you see the interaction by a kind of valley of electrostatic potential between two molecules, here, as you see, there, here, etc. That was one of the first use of the electrostatic potential to describe intermolecular interactions. We have also, but later on, used the electrostatic potential to map the properties of zeolite-like materials, like this one, which is an alpo molecule with aluminum and phosphate atoms here, and you see here that is the static deformation density of the interaction between one aluminum of the zeolite with a water molecule, where you very well see the lone pair in the direction of the aluminum ion. And on the other side, here you see the corresponding electrostatic potential, where you see that the water molecule is really directed along the gradient of the potential, because, as you can imagine, due to the dipole of the water molecule is directed towards the potential. Sure that now, when you want to model our X-ray data, it's very important to do the analysis of the total electron density, which has been made by Richard Bader as first, who proposed this analysis of the topological density, defining critical point where the gradient of the density is 0, calculating the Hessian matrix, and allowing to, in fact, describe the electron densities. He was able, by topological analysis, as you see, to, in fact, define atomic basin in molecule here, and looking to the interaction between two atomic basins through a bond critical point here. From this analysis, we can also calculate the charge and atomic volumes, which are the topological charge and volumes of the molecules. And one important application of the topological analysis is the topological analysis of hydrogen bond. Bader, Mata, Kor, Popelier, and Abramov give the following definition for hydrogen bond. A critical point might be found between the donor and acceptor. Therefore, a bond path should be found in the gradient map. The value of the density and Laplacian at critical point are correlated with the bond energy. One can estimate, therefore, the kinetic and potential energy density at critical point, and the Laplacian at the bond critical point has a positive value. And there is always a mutual penetration of H and A atoms. With Enrique Espinosa, we were able to show a phenomenological relationship between crystal dissociation energy, kinetic and potential energy density. As you see, the correlation and the exponential behavior of the kinetic energy density, the potential energy density, and the dissociation energy density. This paper has been read by many of our colleagues. It is now cited more than 4,000 times. And this has been applied by Piero Macchi to, in fact, understand the metal-alcene interaction, showing by gradient maps that how you can go from a direct ionic interaction to a covalent interaction. And you see that is the bond path, as you see here, from the metal to the alcene bond here, is beginning to split here, then like that, and like that, going from a pure ionic interaction to the covalent interaction. That was one of the first important application of topological analysis to metal-alcene interaction in 1998. We also can map the halogen interaction by Laplacian here, and you see also very well critical point between this cluster of 3 chlorine atoms here, and here. Now I will try to discuss a little the extension of the electron density towards macromolecules. The requirements for protein charge density analysis are, as you can imagine, low thermal displacement parameters. So the B factor, which should be small, no disorder, few solvent in the crystal, and trying to get ultra high resolution. But for a protein, ultra high resolution is much less than 0.5 or 0.6 on 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ charge density for a protein was published in fact 2000. So to try to refine a protein for having some indication about electron density, we had to build a multipolar parameter database, which we call LMAM, which is the first experimental multiple parameter database, which are describing the electron density of the 20 amino acids. And that has been done first by Virginie Pichon in 1995. What we do experimental charge density of mono, di, tripeptide and related molecule, average the PLM, PP, and kappa parameter on equivalent atom, and build this database. And this database now is used to transfer to dataset on protein or more, even a large molecule. And from that, we can estimate the electrostatic potential. Here is, for example, here is an example of the Hellman sp2 electron density. For the sp2 carbon is, as you see here, which is in fact the sum of the oxygen density with the two lone pair here, and in fact the sp2 carbon, and you get here the CO electron density. So from that, we were able to make the first charge density study of a large protein, which was the human aldose reductase, published in CNRS in 2003. At this occasion, we wrote mostly Benoît Guillot and Christian Gelsch, the program MoPro and MoPro Viewer in 2002. It was the PhD of Benoît. But you have to know that MoPro, like ISE, in fact, also, is an extension of the MOLI program. MOLI program is the original Hansen-Coppens program, which itself was derived from the Bussing-Levy ORL-FLS program, which was written in 1962. This program here was, in fact, at that time, very early, to perform least square refinement of crystal structure parameter based on X-ray or neutron measurement. The program, it's interesting to know that the program was written in Fortran to facilitate modification machine. And you see that the fact that it was written in Fortran means also that from in fact, this program, we can use the basis. This program was used to, in fact, develop after the multipolar electron density. Then this MOLI program was originally written by Niels Hansen for a 14-atom organic molecule. And during my postdoc at Philip Koppen's lab, as I was working on porphyrins, I extended MOLI for 100 atoms and adapted it to model the electron density of transition metal for these metal porphyrins. So if you want, is the first charge density study of a large protein, which is the human aldose reductase, which is an enzyme implied in diabetes degenerative processes. It has been published in CNRS in 2003. So the data collection was a huge data collection for that time at the EPS synchrotron at 0.6 angstrom wavelengths. The resolution was minus 0.714 angstrom minus 1. Collected 2,200,000 reflections, 500,000 unique reflections, with an internal agreement of almost less than 3%, and with an average redundancy of 7.5. This data collection was collected by Podjarny, mostly by Podjarny and Joachim Hirsch in IPS. Here is the aldose reductase, as you see, and first independent atom model restraint refinement was made by Schneider. Remember that this is a molecule of 316 amino acids plus NADP plus an inhibitor, which is a total of 6,700 atoms. A third was disordered, and this disorder was not modeled with electron density. At that time, with the independent atom model, the R factor was 9.4%. We use our LMAM database to transfer the electron density and refine the structure. It was a constraint multipolar refinement, and at the end of the refinement, the R factor dropped to 8.9% and a free R factor of 9%. Here is one of the results. As you see very well the static deformation density of a lysine residue, and you see that the map is almost as beautiful as that what we get from a small molecule modeling. So you see also for example, here also, you see the static deformation electron density of the inhibitor after the multiple refinement. The inhibitor was inside the protein, and you see very well a very good electron density of this molecule without any data transfer. The electrostatic potential of the molecule will enable us to prove the electrostatic complementarity between ligand and active site. Here is the active site of the protein without the cofactor. Here is the electrostatic potential of the cofactor. And when the cofactor is going to the active site, as you see, the positive part of the electrostatic potential is going to the negative part here, this positive part also to the negative part here, neutralizing, in fact, the system, and which prove the electrostatic complementarity between ligand and proteins. In conclusion, when we have ultra-high resolution of macromolecule, data of macromolecule, we can see we have a very precise structure. We can see the protonation sites. The multiple database enables the calculation of static interaction energy. And also, you can also estimate the terminally smeared binding energy, as shown by Dominiak and Vosnak later on. I will finish my talk by discussing about what we are doing now, which is a generalized refinement, or joint refinement between charge, spin, and momentum density, and the Molinx program. The scientific objective is the construction of density matrix based on X-ray diffraction data, polarized neutron, and quantum scattering. So what we want to do is to, in fact, use together X-ray diffraction, quantum scattering, and polarized and non-polarized neutron diffraction. For X-ray diffraction, we get, as you know, the electron density, mostly the localized electrons in the bonds. From polarized neutron diffraction, we get the spin density. And from quantum scattering, we are able to model the delocalized electron density. And that's what we have done now, combining these two, but I have no time now to finish. It will be for another seminar. So, to conclude, the future and challenge for crystallographer for the coming discussion. The first form is a challenge are large systems, heavy atoms, which still have no real very good experimental electron density on very heavy atoms. Simple system and extension program, which are still to solve. We can also maybe try to get electron density on metastable states. We have to work on new method, joint refinement, not only with diffraction data, but also with spectroscopic data. For example, following the pioneering work of Professor Dieter Schwarzenbach in Lausanne, who combined spectroscopic data and X-ray data. You should also try to improve our electron density modeling under electric field, under pressure. And I think more fundamental research has to be done on data reduction still, extinction correction, TDS, etc. And that could be done in collaboration with diffractometer companies. So I will now thank all my co-workers and colleagues. Professor Yves Dutossois, who was my PhD advisor, Pierre Becker, who introduced me in the electron density field, Philippe Coppens and Bob Stewart, with whom I worked when I was in Buffalo and Pittsburgh, Bob Blessing, who was not only a collaborator, but a very good friend, Ed Stevens, Richard Bader, Marc Bénard and Marie-Madeleine Moromer for theoretical calculation, Béatrice Gillon for the polarized neutron, and Jean-Michel Dillet for the quantum scattering. My former student, especially Mohamed Souassou, Noureddin Germani, Nicolas Kleiser, Florence Porcher, Christian Gelge, Benoît Guillot, and Enrique Espinosa. I don't want to forget Emmanuel Wenger, who helped me a lot in collecting the dataset. And as you see here, it is a picture of Philippe Coppens with me during the ceremony of Doctor Honoris Causa at the University of Nancy. And it was a very, very nice thing. And I would like to thank you for your attention.
Thank you very much, Claude, for this excellent lecture, excellent overview. And the lecture is now open for comments and questions.
We have already one.
Yes,
we have already one comment from Patrice Kenfak Sopngan. Thanks for the lecture. Please, could you give details about metal-metal interactions? How these interactions are formed?
About metal-metal interaction?
Yes.
So there have been some work in electron density about metal-metal interaction, which I didn't cite in my talk. But if you are looking to the literature, you can find some interesting metal-metal interaction. One thing which is very interesting in the metal-metal interaction, if you have a kind of single bond, is in fact that very often you have no electron density in between the two metals.
We have a comment from Marwan Din Bogera. I'm sorry if I'm pronouncing it wrong. Amazing lecture. Thank you, Professor. We have also a comment from Harita Mambata. Thank you for sharing a nice journey of research.
Thank you too.
And a question from her. Could you please suggest some books to understand the basics?
The best book, I would say, Pierre Becker in 70, which is a Bible for me for theory of electron density. One book which has been written later is from Carlo Gatti and Piero Macchi, Modern Charge Density Analysis, which has been published in Springer. And I think there is some other, but I do not. Quantum Crystallography by Sherif Mata and Lou Massa, published in very recently by De Gruyter. I think you can find some other, but I think the main books are those ones.
Thank you from Harita. Before we see another questions or comments, I have some personal question to you, Claude.
Yes.
Over the years, you've been working on so many different research topics. Is any of these topics special for you? I mean, which of these research paths was the most exciting for you or most important from your personal perspective?
During my career, there were many exciting things, especially when I began to work and to learn from Pierre Becker. That was my very, very important, I think, knowing Pierre Becker, because he was a young professor in Nancy. He came, I was just finishing my PhD, and I learned a lot with him. I think without Pierre Becker, I think I would not have had this career, in fact. Pierre Becker introduced me to Philippe Coppens. I went to Philippe Coppens. I came back and discussed again with Pierre Becker. Really, Pierre Becker for me was my mentor, I would say, more than anyone else.
There is a comment from Patrice Kenfak Soblang. Thank you for the lecture. And a comment from Hansbeth Birgi. Interpreting diffraction data requires modeling electron density and nuclear density, ADPs. You said very little on the latter. What is your opinion on the state of modeling ADPs? And how does this interfere with modeling electron densities?
Modeling ADP is very important. Although you know that what we do very often in our field is to model ADP with high order reflection, where the valence density is almost zero. Another possibility was done, for example, by Philip Coppens with X minus N data, but it was always, for me, it was always difficult to use the coordinate and thermal motion derived from neutron diffraction directly for electron density analysis. Bob Blessing, some time ago, has made a kind of scaling of the UIG, mostly derived from neutron diffraction, in order to be able to use them in electron density studies. I don't remember the reference of the paper, but I can find it for you if you want. But this is the most important problem. Anyway. We need to have very high resolution, and also as soon as we have very high resolution, the data at very high resolution are not of very good quality, which means that it's very difficult also to get very good quality thermal parameters.
A comment from Jean-Michel Gillet.
Bonjour, Jean-Michel.
Thanks, Claude, for this great overview. I fully agree with your opinion on how instrumental Pierre-Becker has been to many parts of charge, spin, and momentum densities. Concerning the density matrix refinement, just to let you know, those interested in this kind of combination of data, I invite everyone to attend Shizuhyu PhD defense on April 24th, 2 p.m. It will be possible to attend online also. Jean-Michel, please then share the link via emails and we'll distribute it.
Thank you, Jean-Michel. We will try to attend it. Can we ask questions also?
No, just a comment. And a comment from Ariste Bolivar Bufak. Thank you, Professor, for the lecture. So many friends among the audience.
Thank you, Bolivar.
Christoph, you are muted.
Claude, I've been very much impressed by your activities in Africa. Can you tell a little bit more about this? I mean, that's very important work. That's something what say European or Western scientists really should help Africa, and you actually do this. So can you tell us more about these activities? They are worth to be say popularized among scientists.
Sure. And you are welcome to help me in this field. So the idea was, in fact, that during my career, I had a lot of African students, and most of them were very good. But the problem was, when they came back to their country, it was impossible for them to do experimental science. Only theoretical calculation was possible. So the idea was to help them to collect data using remote connections. That was what we call the AFRAMED project, which allows African colleagues to collect by internet, using internet, diffracted intensities on our diffractometer. So to do that, we had a contract with CNRS and UNESCO, which enabled us to invite each year during 5 years 4 to 5 students during 1 month. And during this month, they were learning how to use the diffractometer with Dr. Emmanuel Winger, who is in charge of the diffractometers. And from that, knowing how to use the diffractometer, when they are going back to their university, they are able, by remote connection, to really collect their own data. It's important for research, but also a lot for teaching, because our African colleague can show to the student what is a diffractometer first, how it works, and then can interact with the diffractometer. That is very important. It's expensive to continue this project because, as you know, if you run a diffractometer, you have some cost. And before it was the CNRS or UNESCO who paid, but my grant is almost finished now. We will try to find a solution, but if you can help, no problem.
There is another comment from John Halliwell. Great lecture.
Hello, John.
Great lecture, great work. Thanks a lot.
Thank you.
Yes, I must say that I was impressed that Claude managed to arrange like a free space in his lab and also support for all these invited people. I mean, not only 3 of us, but teams of scientists have been invited by Claude to Nancy and spend their very fruitful time. So really, thank you very much, Claude, for these activities. And I must say that also all these conferences, Claude has been organizing lots of them. They bring together our community, and comparing to other groups of chemists or physicists, I must say that our community is pretty good organized actually. And all this commission and really active people on them, they bring people together, and all the conferences, and this fact of this feeling of togetherness is in my opinion, important. I mean, people work in their groups, in their labs, but they know that they have contacts with the other scientists. That's for me, it was very important, and I always value this kind of situation. So actually, what I was doing in Warsaw was to certain degree, I would say, was based on your organization of your lab in Nancy. So thank you very much, Claude.
Yeah, but I think we are in fact for science a small group, and so we need to have a big connection together if you want to survive. In fact, and I think that's very important to continue to interact even with these webinars and all this kind of thing. I think we have to do that because it's difficult more and more to do fundamental science and to be, in fact, recognized for the fundamental science you are doing, because I have to say now, I am retired, so I do this.
I'm getting close to be retired, so I'm really, Anya and Paulina are young. They will take over and continue.
So you have no problem. You have very good successors. No problem.
So what I can say is that you set up a fantastic example that we can follow, and
yes, exactly.
Thank you from the whole community.
Thank you very much.
We have more thanks from Maciej Kubicki. Great, Claude. Thanks a lot for everything.
Thank you, Maciej.
From Pilar Garcia Orduna. Good science is learned, taught, and shared. Thank you very much, Claude.
Thank you, Pilar.
And from Girard Bicon, hello and thank you for from a protein crystallographer. That's from Gerard. And from Emmanuel Wegner, thank you, Claude, for this nice talk.
Thank you. I just have a thing to say, because we are speaking always about quantum crystallography, but I have to say that I do not like this name, because we are not doing quantum physics or quantum crystal or quantum chemistry. So I think the association between quantum and crystallography should be discussed sometime.
Yes, and I hope we will have a great opportunity to discuss it next year at Sagamore conference, which will be at your city, right, Nancy?
Yes.
But improvement of all the tools is leading to studies of quantum, for example, quantum phase transitions and other problems related to, say, quantum mechanics. So it's going there. Maybe this term was picked a little bit too early, but it is showing direction in which many of us go. So it's also there is a big potential in this. With Paulina is smiling because we kept discussing this many times, but I would say that practical applications of this term are very important, and it has appeared to be very useful, and is becoming more and more useful within time. Anyway.
So we have more comments. So we have more comments on that, but before more thanks. So Ari van der Lee, thanks also for your dedication to European Crystallographic Association. From Nicola Casaretto, thanks for your wisdom, Claude. Take care. And from Alessandro Dolmera, thanks, Professor, for your speech. And finally, a comment from Jean-Michel Gillet. Are you pushing to go back to charge, spin, and momentum density? I don't think it made much sense either.
This is like a Pandora box opening.
Yeah, but it does not mean that we are not aware of weaknesses of this term. We are aware, but they are important consequences, and it's really giving direction towards more and more, say, quantum problems, and superconducting materials are waiting for this kind of studies. As I said, personally for me, quantum phase transitions, and that's what I would like to do before I totally retire.
I hope you will succeed.
Okay, thank you very much, really. Paulina, do we have any more comments? Or
no? I think that's all. I do not see any more questions or comments. So thanks a lot, Claude, for this excellent lecture, for discussion, and for your contribution.